Okay, cool. All right. Hello, everyone. I'm Xiaojie Mao from Tsinghua University. Thank you so much for inviting me to this seminar. I had a very great time, presenting this seminar last year with my advisor, Nathan Kallus, who is also here while I was a final year PhD student. And today I'm super excited to come here again to present my recent ongoing project with Guido and Nathan and report some of our preliminary findings, in this project. And here my talk is called Controlling for Unmeasured Confounding in Panel Data using Minimal Bridge Functions from 2 fixed effects to factor models. And in this talk, I will focus on linear factor models in panel data causal inference, which has received a lot of attention in the recent literature. And I will show you how to control for unmeasured confounding and identify average causal effects using the so-called bridge functions that I will introduce very shortly. And I will also discuss about the estimation and inference, for the average causal effects based on the bridge functions. In this talk, I'm going to first introduce the linear factor model setup and also review some existing methods to tackle this linear factor model. And then I will summarize our contributions in this talk. And then I will move on to talk about the identification and estimation of causal parameters based on the bridge functions. And after that, I will discuss about some possible extensions and also the connection of this work to some other related literature. And if time permits, I will present some preliminary experimental results. And finally, I will conclude this talk with a very brief summary. So here we study causal inference in panel data, where we can have repeated measurements or repeated observations for each unit over time within a time horizon. For example, if we want to assess the causal effects of a certain job training program that provides job training services to some low-income people on these people's earnings or income, then we may have connect some panel data where we have some treaty units denoted as A equal to 1 who receive the job training services from a certain time point, like period 0 here. And all of their future earnings might be affected by this job training service. And we also have some control units denoted as A equal to 1 here, who do not receive the job training services at all. And for all of the units, we can observe their outcomes, their earnings, both before the treatment and also after treatment. So people are interested in causal inference for panel data, not just because panel data are really common in practice, but also because this kind of repeated measurement structure provides opportunities to control for unmeasured confounding. For example, if we were concerned about unmeasured confounding in assignments of job training services because they are not randomized, then we may want to leverage this very rich, repeated observations of people's earnings that can possibly be informative for the unmeasured confounding and use them to, alleviate the confounding problem to some extent. And these opportunities motivate a lot of research on many methods like difference in differences, syntactic controls, factor modeling, no-rank matrix admission, and etc. To formalize this causal inference task, here we use this potential outcome framework, where for each unit I at a given time period t, we hypothesize 2 different potential outcomes corresponding to the control option 0 and the treated option 1, respectively. But in reality, we can only observe one of the potential outcomes corresponding to the actual treatment assignment. For example, for the control units here, because they are never treated at all, so we can only observe their control potential outcomes all the time. But for the treated units, we can observe their control potential outcomes prior to the treatment, but we can only observe their treated potential outcomes after the treatment. And here I use pre and post to represent the pre-treatment periods and post-treatment periods. And I use N0 and N1 to denote the number of control units and number of treated units respectively. And in this talk, I'm going to focus on this counterfactual mean for the treated parameter gamma star, which is the expectation of this control potential outcome at time period 0 for the subpopulation of treated units. And we assume that all of the control potential outcomes follow a linear factor model with unobserved factors ui, observed covariance xi, and idiosyncratic errors epsilon it. And here we assume that ui, xi, and epsilon it are IID draws from a superpopulation, and ui and xi have time varying coefficients vt and bt respectively. And we assume that the idiosyncratic errors are exogenous, so that observed covariance x and the unobserved factors u can account for all confounding. But we are now unmeasured confounding in the sense that the factors U can be confounders as well. So if we only condition on observed covariance, then we still have some residual confounding. And we also assume a standard positivity assumption, which means that the propensity scores for both treatment options conditional on all of the confounders have to be strictly positive. And here in our panel data, we can observe the control potential outcomes for the control units all the time. But for the treated units, we can only observe their control potential outcomes prior to the treatment. And in particular, we cannot observe their control potential outcomes at time t equal to 0, which exactly define our target counterfactual mean parameter. So this means that we have to infer this missing counterfactual information from the observed data entries in this data matrix based on this observed data, so that we can identify and estimate the counterfactual mean parameter under the linear factor model. And in the past, many methods were proposed to tackle this linear factor model. And one of the most popular methods is this synthetic control method. And Furman and Pinto pointed out that we would generally need both the number of pretreatment outcomes T0 and number of control units N0 to grow to infinity for the synthetic control estimators to be asymptotically unbiased. And some alternative methods propose to learn the linear factor model structure directly based on using factor modeling or no rank matrix estimation. And these methods also require both T0 and N0 to grow to infinity. So these methods all require big N and big T asymptotics to ensure the identification and the consistent estimation of the causal effects. But we may wonder, what if we only have a limited number of time periods so that the big T asymptotics are not valid here? And what can we do in this case? So in this talk, I'd like to provide you with one answer to this question. And in particular, I will show you a new identification strategy using the so-called bridge functions that can transform pretreatment variables to control unmeasured confounding. And here in this approach, you only need finitely many time periods for the identification and the consistent estimation of causal effects. But we know that bridge functions are usually non-unique in practice, so we propose some regularized estimators to target the minimal bridge function, a very special bridge function among the set of all valued bridge functions. And we prove that the resulting estimator, causal effect estimator, is square root n consistent, asymptotically normal. And we also provide asymptotically valid confidence intervals. So in summary, we're going to provide a novel approach for causal inference in panel data under the linear factor model that only requires large n small t asymptotics, which complements existing approaches that require large n and large t asymptotics. All right, so now let me talk about the identification of the causal effects based on the bridge functions. So here, let's first start with the motivating example in the two-way fixed effect model, where we have unit fixed effects UI, the time fixed effects BT, and also the idiosyncratic errors epsilon IT. And this obviously is a special example of the linear factor model where the coefficients for the unmeasured confounders UI is just a constant 1. And we only consider the constant 1 as a covariance without any additional covariance. And in this model, it is very well known that the difference in difference estimator, the DID estimator, can estimate the counterfactual mean parameter consistently. And this estimator consists of 3 terms here. One is the average of the treated units pretreatment outcomes, and the second one is the average of control units pretreatment outcomes, and the final one is the average of control units outcomes at time t equal to 0. If we take a closer look at this difference in difference estimator, we can see that it's essentially a sample analog of this population estimand that consists of these 2 terms, and each of the terms here is just a population limit of the corresponding sample average terms in the DID estimator. And based on this, population estimand, we can actually reformulate this into a conditional expectation of a linear transformation of the pretreatment outcomes, conditional on the subpopulation of treated units. And this linear transformation of the pretreatment outcomes is enough to control for all unmeasured confounding, so that its conditional expectation can recover the true counterfactual mean parameter. So by this reformulation, we can see that the DID estimator is essentially learning such a transformation to adjust for unmeasured confounding in order to estimate the counterfactual mean parameter. And this motivates us to think whether there also exists some transformation like this that can adjust for the unmeasured confounding in the linear factor models. And here, to think about these transformations, let's first take a look at the unmeasured confounding effects in the linear factor models. So we know that the unmeasured confounding effect on the targeted control potential outcome Y00 is just U transpose V0. And also the unmeasured confounding effects on the pre-trim outcomes are given by the U transpose and these V factors in the pre-treatment periods. And we concatenate these factors into this V pre matrix. And we can see that if we can find a vector theta 1 star that can solve this linear equation system, then this theta 1 star would be able to linearly transform the unmeasured confounding effects on the pre-trim outcomes to exactly match the unmeasured confounding effect on the targeted control potential outcome. And as a result, this theta 1 star parameter, coefficient would induce a linear transformation of the pre-trim outcomes and also the covariance X, such that the unmeasured confounding effects on this transformation is exactly the same as the unmeasured confounding effect on the target control potential outcome. And we call this kind of transformation as a bridge function for the linear factor model, because it sort of bridges the unmeasured confounding effects on the pre-trim outcomes and the confounding effect on the target control potential outcome. And here the existence of bridge functions of course depends on the existence of solutions to this linear equation system that consists of R many linear equations for capital T0 many unknowns. And if the coefficient matrix here has full row rank, which is equal to the number of unmeasured confounders R, then we would have solutions to this linear equation system. So bridge functions would exist in this case. And this rank condition, of course, is very crucial here. It implies that the number of pre-trim outcomes, capital T0, has to be no smaller than the number of unmeasured confounders R. It also requires that the pre-trim outcomes are very informative proxies for the unmeasured confounders, so that their unmeasured confounding effects can basically capture the variations of the confounders U along all possible directions, so that they can also capture the confounding effect along this direction V0. And this is the reason why the linear transformation of the pre-trim outcomes can totally adjust for all unmeasured confounding in the target outcome. So here, based on these linear bridge functions, we can show that actually they can recover the counterfactual mean parameter. Especially here, we know that the treatment is assigned after the pre-treatment outcomes are realized. So the treatment assignment has no direct causal effect on the pre-treatment outcomes, conditionally on the unmeasured confounders U and the covariance X. And we can prove that under this condition, any valid bridge function that satisfies this conditional moment equation would be able to recover the counterfactual mean parameter according to, through its conditional acceptation. So here we establish the relationship between the bridge function and the counterfactual mean parameter, but we still don't know how to learn this bridge function from observed data because they depend on these unknown parameters, the V parameters and also the B parameters. To learn the bridge functions from observed data, here we need to assume some additional assumptions. And the first condition is that the idiosyncratic arrows in the post-treatment periods are independent with the arrows up to time t equals 0. And under this condition, we can prove that the post-treatment outcomes are conditionally independent with the outcomes up to time t equals 0 given X and U, which means that the dependence between post-treatment outcomes and these other outcomes can be fully mediated by the unobserved confounders U and the covariance X. And we also assume that this second order moment matrix for U and X is invertible, which means that the components of U and X are not collinear. And we additionally assume this block matrix to have a full column rank, which requires the post-treatment outcomes to be also informative proxies for the unmeasured confounders, so that after accounting for the effects due to the observed covariance, the unmeasured confounding effects on the post-treatment outcomes can also capture the variations of unmeasured confounders along any direction. So under these two conditions, we can prove that any valid bridge function, any transformation of the pre-trim outcomes and the covariance X is a valid bridge function if and only if it satisfies this marginal moment equation formed by the post-trim outcomes and observed covariance X. And this theorem is really nice because it means that for any solution to this moment equation that only depends on the observed data, the solution theta star would correspond to a valid bridge function whose condition expectation can recover the counterfactual mean parameter. So this means that counterfactual mean parameter is fully determined by the distribution of the observed data. So gamma star here is identifiable. So in summary, I show you that when the pre-trim outcomes and post-trim outcomes are sufficiently informative about unmeasured confounders U, and under additional conditional independence assumption about these treatments, we can show that the parameter gamma star is identifiable. And importantly here, if the unmeasured confounders have small dimension, then we only needed a relatively small number of pre-trim outcomes and the post-trim outcomes to control for all unmeasured confounding. And we do not need them to grow to infinity in order to achieve identification. So here I show you that the gamma star parameter is identifiable. And in the next part, I need to tell you how to estimate the counterfactual mean parameter based on the bridge functions. And from the next part, I show you that here we mainly need to solve these two sets of moment equations corresponding to the bridge function coefficients and also the counterfactual mean parameter respectively. And then we also know that the set of solutions to this marginal moment equation, this first moment equations, is exactly the set of valid bridge functions given here. And here we can observe that whenever the number of pre-trim outcomes, T0, is strictly larger than the number of unmeasured confounders, we would have infinitely many solutions to this linear equation system so that we have infinitely many possible bridge functions that can account for all possible unmeasured confounding. And this, of course, means that we would have infinitely many solutions to these first moment equations. And in this case, if we just apply standard estimators, like the generalized method of moment estimators, to estimate the bridge function coefficients, then these estimates may not necessarily converge to any fixed limit because there are infinitely many valid bridge function coefficients. And this set of bridge function coefficients is actually unbounded. So standard GMM estimates can be even very unstable. And its performance can be very bad in practice according to our numerical experiments. So this really makes the estimation and the inference very challenging. And how should we deal with these non-unique bridging functions here? So to handle this challenge, let's recall this two-way fixed effect model again. And here we just give you the set of bridge functions for the two-way fixed effect model. And here we can see that whenever the number of pre-trim outcomes is strictly larger than 1, then the bridge functions for the two-way fixed effect model are also non-unique. And the DID estimator just picks a particular simple bridge function coefficient among the whole set of valid bridge function coefficients. And this is really quite cute trick. And it motivates us to think, why not we just target the particular bridge function among the whole set of bridge functions in linear factor model? And this is exactly what we propose to do. So here we propose to target the minimal bridge function whose coefficients can achieve the smallest L2 norm among the whole set of valid bridge functions. And we propose to estimate this minimum norm coefficient by using this regularized generalized method of moment estimator, where we have an L2 regularization term for these coefficients, which of course encourages small norm solutions to these moment equations. And once we obtain this regularized estimator theta hat, we can plug it into this second moment equation to solve for the estimator gamma hat. And we prove that this gamma hat estimator, based on regularized GMM estimation, is actually asymptotic linear with a closed form influence function that depends on the minimum norm solution of the bridge function moment equation, and also the true counterfactual mean parameter gamma star and the limiting weighting matrix here. And based on this, we can show that the gamma hat is square root inconsistent, asymptotically normal when the regularization parameter num n converges to 0 at a suitable rate. And we can easily plug estimates for these unknown parameters into the inference function and use that to construct an asymptotic variance estimator, which would lead to an asymptotically valid confidence interval. And finally, we prove that the smallest asymptotic variance among the whole class of regularized GMM estimator can be achieved by the inverse covariance matrix using the inverse moment covariance matrix as a limiting weighting matrix. So here, proving the theory is highly non-trivial and took me quite a while, to figure out how to prove this. But the result is quite remarkable because it means that our estimators are fully robust to the non-uniqueness of the bridge functions. If the bridge function happens to be unique, then this just reduces to the standard GMM estimation theory. But if the bridge functions are non-unique, our estimation theory here still holds, whereas standard GMM estimation theory would fail. So next, I'd like to very briefly mention that we also extend this approach to allow time-varying unmeasured confounders, where the confounders themselves can also change over time according to an autoregressive process. And we derive conditions that ensure that we can use bridge functions to identify the counterfactual mean parameter in this case. And finally, I want to point out that this approach is closely related to the analytical control framework proposed by a recent series of works by Ari Chakchagan and his co-authors. And we found that it's actually also discovered independently by Dinner. And these are really amazing works, and I highly recommend you read them. And here in this synthetic control framework, we have two types of proxy variables for the unmeasured confounders U. One type is called analytical control outcomes W that are not affected by the primary treatment A here. And the second type is called analytical control treatments that do not affect either the primary outcome Y or the analytical control outcomes W here. And the concept of the bridge function also originates from the paper by Mao and Chagin. And in our panel data setting under a linear factor model, we have very natural analytical controls here. And we can see that the pre-trim outcomes can be used as analytical control treatments, analytical control outcomes, because they are not affected by the treatment assignment. And the post-treatment outcomes can be treated as analytical control treatments because they cannot directly affect these outcomes that are realized after post-treatment outcomes. And here we can show that the pre-treatment outcomes and the post-treatment outcomes are valid analytical controls when the confounders are either time invariant or time varying. So here we can basically view our identification strategy as application of this analytical control framework into this linear factor model that has been very influential in the panel data causal inference. But we propose a novel estimator to handle the problem of non-unique bridge functions, which should be quite common in practice. So this also sort of fills in a gap in the analytical control literature. So for the interest of time, here let me just ignore the experiment part and just go directly to the summary. So in summary, here we consider a linear factor model for panel data causal inference, where we have either time invariant confounding or time varying confounding. And here we propose to identify average causal effects by using bridge functions that can transform pre-treatment variables to control for unmatched confoundings. And here, importantly, our approach does not need the number of time periods to grow to infinity. We just need the number of time periods to be enough to account for unmatched confounding. And because the bridge functions are usually non-unique, we propose the regularized estimator to target the minimal bridge function. And we prove that the resulting causal effect estimator has desirable asymptotic properties, no matter if the bridge functions are unique or not. And finally, I want to stress that our approach does need additional assumption, the assumption that requires the post-treatment outcomes to be conditionally independent with the pre-treatment outcomes, given the observed covariance X and unmeasured confounders U. And this assumption is not necessarily assumed in existing methods. So we should view our method as a complement to existing methods that require nudge T and nudge N asymptotics. So that's all for my presentation here. Thank you very much for listening, and feel free to ask me any question.
Thanks, Xiaojie. So we currently don't have any questions, but maybe we can wait a bit and see if any come in. And also feel free to raise your hand if you want to, anyone wants to ask their question live. Oh, we have someone raising their hand. Oh, Alex, feel free to unmute yourself.
Yeah, absolutely. Thanks so much for the talk, Xiaojie. This is super interesting work.
Thank you.
Whenever we sort of have discussions about these negative control strategies for adjusting for unmeasured confounding, I'm always curious about whether there is a sort of intuitive interpretation of the rank conditions that are necessary for that system of equations to have an appropriate solution, because those seem to be sort of the key assumptions that enable adjustment for the unobserved confounder. So here, do you have an intuitive interpretation, or maybe some sort of like cartoon examples of when we might think that this assumption holds versus when we think the assumption might fail?
Yeah, sure. So thanks for the question. So the question here is my understanding about when this rank condition can hold. Of course, mathematically speaking, this rank condition just means that the unmeasured confounding effects on the pre-treatment outcomes can capture all directions of the confounders, which means that the pre-treatment outcomes have to be sufficiently informative proxy variables for the unmeasured confounders, which makes sense, right? Because they have to contain enough information. They have to be able to recover all of the information about the unmeasured confounders. Otherwise, there's just no way to control for all unmeasured confounding. And another way to reason about this is that basically we need first of all, we need a number of pre-treatment outcomes or the proxy variables to be no less than the number of unmeasured confounders. So its dimension have to be higher. And secondly, if we consider this linear factor model, the noding of the unmeasured confounders on the pre-treatment outcomes have to be at least, how should I say? They should manifest them independently and at least are many pre-treatment outcomes or are many network controls. So I think that's kind of the interpretation for this rank condition. And for more general setting, where we don't have this linear factor model structure, we don't have this linearity structure, it's going to be even harder. Like if you look at the general network control literature, then they usually need some sort of complex conditions which are harder to interpret, and that's why I also particularly appreciate this kind of linear examples.
Okay, thanks, Xiaojie. I don't think